Okay, perfect. Well, welcome everyone. We're excited to have you. Happy afternoon, or if you're somewhere outside of the US, happy whatever time of day it is for you. On the webinar today, we're going to focus on using Lake Oroville as a case study to understand recent extreme weather and the role that forecasts can play, in particular, a new generation of streamflow forecasts to help water resource managers make better decisions. So just as a quick overview of how we're going to spend the time, we'll quickly introduce ourselves, why we care about these sorts of things, and then take a look at what's happened at Oroville over the last 5 years and talk about a bit why we think that matters, why it's exemplary of other trends, and then look at different forecasting approaches, both traditional ones and some of the work that we're doing here at Upstream Tech, and then circle back to Oroville and actually apply some of our new methods to Oroville over the recent years, and then save some room for discussion at the end. So hopefully we'll have about 5 or 10 minutes for any questions or discussions you have. I'm joined today by my colleague, Laura Reed, who's our HydroForecast product manager, and I'm Daniel Palmer. I lead our growth and partnerships. So we are about a 25-person company, and I like to describe the way that our team is made up as sort of reflecting the way that we approach our work. So it's a combination of experts in software engineering and machine learning. And then we have domain experts as well. So water resource engineers, environmental scientists, and the like. We have 2 main services that we focus on. Today, we'll be talking a lot about HydroForecast. Our other product is called Lens, and that helps folks understand changes in landscapes over time using a combination of satellite and aerial imagery, as well as in situ monitoring tools. As a company, we work with a couple dozen organizations. They range from utilities to public agencies to NGOs. Within HydroForecast, right now we're forecasting at about a little over 300 different streamflow points, and that represents about 4 gigawatts of hydropower capacity. So with that, let's turn to sort of, our recent work in the area. I think our group today is pretty American West heavy. So wanted to call out some of our relevant work in the area. Right now, we're forecasting at about 24 sites for customers and partners in the West, as well as creating historical flow records for about 300 different sites across California, both some that have gauges and some that don't. We recently finished up a year-long forecast sort of competition that evaluated our forecasts against NOAA's and other teams' in-house systems, and found that HydroForecast was the most accurate forecast available. That included 9 sites in the American West. And then as you'll see here on the right, we just launched what we're calling a regional outlook that shows 1 month ahead forecasts for California's 5 largest reservoirs. That's currently in beta, and we're looking for folks who are interested in testing it. So I'll come back to this at the end, but if you're interested in what flows are going to look like in California 1 month ahead, please reach out. We'd love to have you as a beta tester. All right, so Lake Oroville, the reason everyone's here. So to start, why do we care about Lake Oroville? Apart from the fact that it itself is really meaningful, we think Oroville tells a story that's actually really representative of a lot of broader trends that are going on as well. Some of that is just Oroville is so connected to the importance of water and water risk more generally. So as you can see in this headline, obviously it's a huge source of power for the state, but it's also really important for water delivery to municipalities, for agriculture, for a number of other uses, for environmental purposes. And then the second is that what we see happening at Oroville, we think is not happening just at Oroville. So more broadly, the American West is expected to get drier and drier, and the East is expected to get wetter. So what that means is that what we talk about as extreme conditions are actually becoming less and less extreme and more common. Within Lake Oroville, the last 10 years have been pretty crazy. So if you look at 2011, sort of that was a generally standard year on the early end, and you can see this picture on the far left. After that, there was a pretty significant drought that lasted into 2017. But then in 2017, there were record flows, and the dam nearly failed due to a very large event. Now we are today at record low lake levels. So you can see the bridge from that picture in 2011 is now much higher above the water in 2021. So Oroville is really demonstrating how much variability is coming into water systems. Looking at it not just from pictures, but actually from a hydrograph, you can see this dotted black line showing sort of the annual cadence of the long-term average with the spring pulse and the recession as it goes into the fall and winter. The blue line here shows what actually happened. You can see it doesn't track very closely to the long-term average. You have big spikes, like in 2017, going about 5 times above what you'd expect that time of year, down to, if you look at the last 2 years, very minimal flows compared to what you'd need. And that's obviously important because this water is so valuable and plays such a strong role for so many different groups. Some of what we're seeing here is that historical patterns just aren't holding true. So we're seeing common droughts and the dry years are becoming more frequent. But even beyond that, the relationship between weather and what we get as inflow are changing. So looking at this year, if you were to take the snowpack that was measured on April 1st, the overall inflow into the system was actually about 20% of what you'd expect based on that snowpack. So as we think about forecasting going forward, it's really important that we realize and think through what ways we can capture all of the different relationships that are changing within basins and be able to make more accurate forecasts going forward. I'm going to spend just a couple of minutes talking about traditional seasonal forecasting methods. There are a bunch of different ways to do this, and we're certainly not going to cover all of them. I'm going to just focus on one to use as a bit of a case study. So what you have here is essentially the approach that the Bureau of Reclamation uses for their 24-month forecasting. And basically, they look at the current conditions. So thinking about how much water equivalent is expected to be within the snowpack, what current flows are, other variables like that. And then they take each of the past 35 years and say, okay, let's run through what happened between April 1st and the end of the season. And let's apply that to our current conditions. And then at the end, you get a distribution of flows, everything from the most common years down to the extreme wet and dry years. Now, this has historically been, one of the better approaches that we've had to be able to understand flows, but there's some limitations. And so what I'm quoting here and on the next slide are some findings from a recent study that looked at, okay, California was a really tough case this year. What happened and what went wrong? The first is that these old rules of thumb are less reliable. So they assume that this year has an equal likelihood of being sort of within any of the past, say, 35 or 50 years. But we know that's not true for a couple of reasons. The first is that you have normal variations across years. You have things like El Niños or La Niñas. But we also know that overall, trends are changing. So 2021 in California was the 3rd driest year on record, and 2020 was the 9th. We hear this with our partners all over the country. In the Southeast, it's, our 4 wettest years were the most recent. But overall, these sort of historic conditions are not staying true. So the future is not expected to actually be like the past. The second limitation of this traditional approach is that there's actually a lot of new science coming out that's bringing new forecasts, new data, and making things available and making them much cheaper and easier to use. And so when you don't bring those in, you actually leave a lot on the table of what you could be forecasting. So their solutions are pretty straightforward. It's what you would expect, understand that it's important to know within a model what all the different processes are that are influencing runoff and inflow, and try and incorporate those into your models. And then the second is bring that new data, bring those new forecasts into your models, apply them so that you're using the best available science when you're doing your forecasts. That's probably easier said than done. So with that, I'll turn it over to Laura for a few minutes to talk about the work we're doing at HydroForecast and how we're incorporating these new methods.
Great, thanks, Daniel. Yeah, so I will dig into our model and the offerings that we provide through HydroForecast. and then get into some details on our forecast for Oroville over the last few years. So just at a high level, HydroForecast is a streamflow model, and we have two offerings that are forward-looking, both at a short-term horizon, which we call our 10-day forecast, and that's at an hourly resolution. And generally that's for operators, flood management, things that are happening on that shorter time scale. And then we also have a seasonal product that looks out 60 days and even beyond that, to more help with decisions that are made on a water allocation, water management, water supply timescale. And then our third product is actually a look back product. And we've used this to create historic estimates of streamflow where there are no gauges. And we worked with environmental partners, especially in California, but also beyond that, to understand how creating these streamflow records can assist with environmental flows planning, habitat protection, and decisions more on the environmental side. So yeah, if you go to the next slide. So high level HydroForecast, we really created this product recognizing a couple of things. We're excited about it because over the last decade or even more, there's been a lot of advancements in data, how we can process data, what data are available through satellites, more weather models coming online. And so really recognizing that there are some advancements and things that we can leverage from just the data science side and availability of data, and how cloud processing and computing can allow us to access things within the hydrologic processes that we may have not been able to do before. And so what we do is basically combine those advancements in data processing, availability with a machine learning approach to modeling hydrology. And that approach that we use, we call theory guided, because we are able to, and we focus on ensuring that our model is learning hydrology through the data that it's being ingested, and not just memorizing patterns through basic machine learning. So we instill some limitations and constraints on the model so that it truly is learning hydrology, and then we validate that it's doing so by digging into the model. Yeah, and so just how it works, this is a general slide and we can dig into the technical details as questions come up, but basically what we do, our approach is to train a core model. And what that means is that we have a model that has seen hundreds and hundreds of basins across the US and beyond that. And so at that level, the model has seen how weather interacts with certain topography, interacts with certain soils and things like that. And it learns how different precipitation that's coming through a system will translate into runoff or will infiltrate, and how runoff really relates to the inputs. And that's really powerful because it means that when we have this core model, we can go to a new location, give it satellite observations and basin conditions from that local area. We can give it in situ gauge measurements, so streamflow gauges that are historic records in that area, and then weather forecasts that are for that region. And the model will actually learn and knows how to translate that into streamflow or store it in the basin. If you go to the next slide. And so just to give you an idea of what that can actually look like, for example, we pull in MODIS satellite data, which is near daily, and we pull that in from the vegetation index, snow index, and then we also pull in SNODAS data. And basically that's giving the model a picture every single day of how the basin is changing. And if you think about a typical process hydrologic model, essentially that model, the way that the model learns in that system how to translate precip into runoff is by parameters. And so you say, okay, for this vegetation type, the infiltration parameter or the leaf area index parameter, things like that, associate with this amount of runoff. And so you parameterize it from a physical side. What we do is actually just feed the model these pictures of how the basin's changing. And so if you can imagine here in February, this is the site in California, it's not very green, it's barren, there's some snow on the ground. And every day the model gets that picture along with the temperature, along with the precipitation, along with many other variables. And it learns based on the historic record of streamflow in which it was trained when runoff is occurring and when it doesn't. And thinking about doing that at scale across hundreds of basins, you can imagine it's pretty powerful for the model to then learn streamflow. And that's how we get such accurate predictions in our model. This picture on the right is from July. And so, by the time July arrives, all the snow is melted and the basin has greened up, and the model understands that now, okay, the soil is saturated and runoff is going to occur, and the temperatures are above freezing. And so we don't have that storage happening. Can you go to the next slide? Another way to look at it, this is from our dashboard. We're showing at the top there, snow water equivalent, that's from SNODAS. In the middle is the MODIS snow cover. And then at the bottom is the MODIS vegetation index. And one thing that's kind of cool is just seeing, okay, these are two different snow products. The blue band and the blue dotted lines are the long-term average, or what you would expect for those different months of the year. And this was so far in 2021. You can see they kind of go to zero. So both products are aligned on when the snow actually melts out. And at that same time, the vegetation or the greenness is picking up and then continues to go on through the later part of the year. And so the model is actually seeing those patterns and learning that, and then helping to translate that into runoff streamflow. Cool. So this is an example just of what our actual prediction looks like at a site. This was during Hurricane Ida at a southeast site, and our short-term model here. So we have a 10-day forecast. And one thing to note here is that our model, actually how the architecture is set up, is we are predicting a full probability distribution. So our mean prediction is that dark line in the center, and then our 50% confidence interval and our 90% confidence interval is surrounding that. And so for those who are interested and able to incorporate uncertainty into their planning, this can be really helpful context and information. And then I'll just say the other thing about it is the way that we have our model set up is that we feed in multiple weather forecasts into the model at once. And so as Daniel was talking about, one way to do it is you could run traces. So you could say, okay, give me the NOAA GFS forced prediction, give me the ECMWF forced prediction, and then you can kind of draw inferences on where the uncertainties are in between that. But we actually let the model handle that itself, and the model learns when to trust which weather source. And if those two weather sources are disagreeing, it will respond by increasing the confidence bounds, because it says, actually, there's some uncertainty here in the weather forecast, and we're going to translate that into the streamflow forecast. And that's really, what happens when the weather forecasts are disagreeing. We've all seen it. You have one source that's saying one thing, you have another source that's saying another thing, and it's up to us to understand what's really going to happen. But the model can actually do that as well. And so we're passing on some of that burden to the model. Cool. So I think in the next, so just to wrap up this section on just what our model is about and our approach, essentially what we have focused on is seeing a gap in the forecasting research and literature and community, where taking a lot of big data, processing it on our own, and feeding those images into the model from satellites, as well as multiple weather forecasts, really gives us a strong core model that can be basically scaled across the country and across the world. Our model ingests global inputs, and we have some inputs that are US based, such as the NOAA high resolution rapid refresh weather forecast that we can use in the US, but isn't available everywhere. But our model actually, the core model is trained on only global sources, so that we can go anywhere in the world to produce a forecast or a reanalysis. And then, of course, the other thing that we do is then use transfer learning to say, okay, our core model has all of this knowledge and information, and let's go use that in a new location. Cool. So switching gears a little bit here and digging into what our model, our seasonal model, has shown across Lake Oroville. If you go to the next slide. So here's what I'll just explain this graph a little bit. So the red line is the HydroForecast prediction. And what we've done for each of the series in this plot is we've said, okay, what's the 30-day ahead forecast? And then we've put those together to get a continuous time series. The observed line is in black, and then the long-term average is the blue dashed line. And of course, you'll see that repeat every year. So from 2017 to 2021, this was our validation period of the model. The training period goes back to 2000. And so this is basically, the model did not see any observations. It wasn't even trained on this basin. So it had no information about what Oroville as a drainage basin, the characteristics. It had never seen this time period. So it couldn't know that 2019 was a wet year. It didn't know that 2020 and 2021 were dry years. And so these are the predictions that came out from that 30-day ahead model. And essentially to summarize in terms of error, HydroForecast had a 50% lower mean absolute error, and then a 45% lower root mean squared error than if you were to just use the long-term average as a predictor for what occurred over these last 4 years. And specifically in spring 2021, so this is the same idea of the plot where you're looking 30 days ahead, and this just zooms into the period that was the winter of 2020 all the way to July of 2021. And you can see our mean prediction there, a little bit higher than the observation. But basically, if you compared that to the long-term average over just this period, we had a lower mean error than 80% lower than the long-term average, and then a 78% lower root mean squared error than the long-term average. So definitely able to show some skill and value in looking 30 days ahead over this area. A couple more plots here. So another way to look at this or think about this information is, what if you had a forecast that updated every single week over the really important time of the year? And so if you look across the x-axis there, what we're showing is every week we're updating the month ahead forecast. So on March 1st, 2021, we make a prediction for the next month. And then on March 8th, we update that prediction and we go out all the way. And this is just a snapshot to show that peak period. If you call it a peak, it was so dry. But so the blue is our box plot. So I was showing the mean prediction on the last two plots, but what we actually provide, just like the short term, is a full distribution of the possible flows in that month. And so you can see that the line across the solid line is the median. And then those whiskers are encapsulating our 90% prediction. And so following those boxes, the model was more uncertain in the beginning and then kind of narrowed as we move through May. The stars are the long-term average. So the long-term average was, as we saw in the last plot, expecting, you'd expect higher flows. And then the actual observed inflows are those pluses. And so looking at the mean prediction, from the last plot, we were a little bit high, but if you are able to think about it in terms of, are we within the prediction of the model, the full prediction, then the model actually did a pretty good job. We were a little high there at the beginning of May, but in general, within the 50% range of that interquartile box. Cool. So one last plot here. I mentioned earlier that we consider our approach theory guided. And one of the ways and reasons that we do is we like to look at what drives the model. So one thing about machine learning models is that they can be, a bit of a black box. And we sort of open up that black box and investigate what the model is doing and why it is doing that. And one way to do that is to actually look at the inputs that are driving particular forecasts. So what we're showing here is in the top plot, if you look at the dates there, we're tracking what the model was given and what it was seeing from December all the way to when it made a forecast on March 1st. And you can barely see there's a green dot. Daniel, I don't know if you can move your mouse over it. There's a green star on March 1st in the bottom plot. And that is like our forecast. And so everything before that is what the model was seeing. So the GEFS, that's NOAA's GEFS, the temperature is in red, and you can see it kind of hovers around freezing, and then it's warmer, and then it goes down to freezing around late January, and then it goes above freezing. And so that's, typically understanding that temperature pattern along with the precipitation pattern shown in blue is a way to understand, okay, is the precipitation falling going to come as snow? Is it going to come as rain? And that will also drive runoff. And so if we follow that pattern, we see that's what the model was looking at. We see the discharge. So in the bottom plot there, we have the observations in dark black, and those are aggregated to the 30 days, to the week. And then we have the actual raw observations in the gray lines. And if you hit next, what we do then is we actually look at which inputs contributed the most to that forecast that was made on March 1st. And you don't have to look at every single one of these colored lines. Really, the purpose here is to show, okay, what were the most important inputs? And the way to see that in this plot is to say which of these inputs deviates most from zero. So this is the y-axis is called an integrated gradient. I won't get into the details there, but the higher or lower the value is from zero, the more important it was to the model. And so that blue line is the GEFS temperature, and that dark maroon line is the GEFS precipitation. And then that green line is the 16-day median value from the MODIS snow cover. And those inputs make sense to us. We saw precipitation, we see temperature, we know that influences runoff and streamflow. We know snow does at this time of year. And so basically this is a way for us to understand whether the model is tracking the right processes and which inputs are actually driving the forecast. And so we do this a lot with our partners and any time that we are making predictions. Yeah, and so that's essentially the end of just looking at Oroville for the last few years of what we have predicted, and I'll pass it back to Daniel to wrap up.
Awesome, thanks, Laura. So yeah, I think hopefully everyone's still with us. I know we've shown a lot of plots over the last few minutes, but why does all this matter? Why are we spending our time doing this? I know a number of the folks who called in, you all spend a lot of time on modeling and finding good models. So what's the takeaway of all of this? I think the first thing that's really important to us is that this is not just an academic exercise. So we publish what we're finding along the way, but the overall goal is to advance the field. And we think that this is really important because it means that what we've done with HydroForecast can actually support water resource managers, and it can help them make better decisions that they're more confident in, and they can do so sooner. As Laura was showing, HydroForecast isn't as tied to what has happened in the past in a specific basin, but is able to understand general relationships across hydrology that can be applied into this changing world that we're in. And that's really important for folks who are trying to make better decisions. We recently saw some validation of this for a short-term model. So we spent about a year with this competition that the Bureau of Reclamation and CIADI set up, where they said, okay, let's look at about 24 sites and create a competition to evaluate who is able to give the most accurate forecasts. And this included the river forecast centers, the National Water Model, a number of other large organizations had their own forecasts in there. And the main takeaway is that all the stuff that Laura just talked about actually works in practice. It's able to give really accurate predictions, both in general, but also for specific circumstances. So getting high flows right, getting flows at further time horizons right, reducing bias overall. And I think that's been a really important piece of validation for knowing that these systems are ready to go. They're ready to be used. And so our overall goal is to help water resource managers, whether it's conservation organizations or hydropower producers or public agencies, be able to make better decisions, as what used to be considered extreme is now much more common. And there are a few different ways that we tend to do that with folks. So we can always just deploy our models operationally, both our short-term or our seasonal models. With new partners, we're typically ready to go within 90 days. So once we agree to work together, within 3 months, we can have forecasts up and live. The second is looking at different ways to collaborate around research. So we have a number of national labs and NGOs that we often will go out and we'll seek funding to conduct research or to publish together. And then a third way is just if you're in California and you're interested in what flows look like at the 5 biggest reservoirs over the next month, we'd love for you to be a beta tester for our regional outlook. So feel free to just shoot me an email at daniel@upstream.tech, and I'll just drop a line to say hi to everyone after this anyway, so you'll have my email. But if you'd like to give us any feedback and participate in making that something that's as useful as possible, we'd really welcome that. So we've still got about 10 to 15 minutes. Thanks for hanging with us through this, and happy to answer any questions that folks have. So we've got a couple that have come through already, but if you have any other questions, feel free to open the Q&A box at the bottom or top of your Zoom, however it's set up, and just drop us a question. Okay, sounds good. One of the first questions is, do you have examples of other extreme events that HydroForecast has predicted? Yeah, one of the sort of going back to that streamflow competition, I'll jump back to this slide. So one of the fun things about this was that we got to see HydroForecast sort of in action at a number of different sites. During the validation period, so part of our sort of testing period to see how the models would do at the sites in Quebec was what was then considered a 1,000-year storm. It was the highest flows that had ever been seen on the Rouge River in Quebec. And HydroForecast was able to pretty accurately capture both the rise and the peak, the overall magnitude, and then also the limb and the recession of what happened with that event. On the flip side, we're doing some other work in California right now about extreme low flows and being able to accurately predict, when flows are below 50 CFS or even lower, how accurately you're able to capture that. And maybe Laura, you could speak a little bit more to that.
Yeah, I think that's a good example. I think if you go back to that plot showing our short-term forecast, that was an example of Hurricane Ida at a southeast site where the flows not only were really high, but if you can see the previous 7 days, and so it really jumped up quite a lot. And the timing and magnitude that the model was able to capture was we were really happy with.
Great. Awesome. Another question. If I were interested in using HydroForecast at my sites, what would I need to send to get started? Do you require historic gauge data? Perfect. So the short answer is we need to know the locations that you're interested in forecasting and the horizons on which you're interested in forecasting, whether short-term or seasonal or both. From there, the model is able to make a pretty accurate prediction. And then if you have any local in situ or historic gauge data, we're able to bring that in and help the model train it to be even better from there and run forward from that. So that takes about 90 days typically, or sometimes even less. I know Laura manages our product team, so I won't say that it's much faster than that while she's on the line. Perfect. Okay. Another question. At what time step does your seasonal model ingest data? Laura, do you want to answer this one?
Sure. Yeah, we have a number of different inputs for the seasonal model. So one of them is the satellite data, and we actually ingest that. That's almost daily. There's a little bit of a lag on it. So that's daily data. We ingest any observations, so any stream flow observations from, let's say, USGS or DWR, Those could be daily predictions as well, daily ingest. And then we have other inputs like climate indices, so like the El Nino oscillation or the PDO, things like that, that are a little bit longer time scale, and we're able to ingest that as well. And then our weather forecasts that we use ECMWF, we use GEFS, we use GFS and CFS. Those are all different climate products, and they have updates every 12 hours, generally, the GEFS and the GFS. So we're incorporating those. And then they go out to different time horizons. So GEFS, for example, is 35-day product. So we're ingesting it as long as we have it. CFS goes out even longer. So we're ingesting that for as long as we have it. So yeah, the model is able to take in different input frequencies as well as horizons.
Perfect. All right. One more question is, first talking a little bit about the regional outlook. So a question of which reservoirs is it at and at which horizons? Laura, do you want to run through that? So I pull up the...
Yeah, the regional outlook is, like I think Daniel said, a product that we're excited to roll out and get feedback on. What we're attempting to do here is basically provide an overall view of what's expected and what's happening right now in California. The 5 reservoirs that we have here make up about 80% of the inflows into the State Water Project and into the Central Valley Project. And so they're really important for understanding how allocation and how water supply may look in the important season. And so what we have is our prediction over the next month across all of the reservoirs. That's that box plot there to the left of the map. And then as well as the total inflow forecast, we also have precipitation and air temperature. And so we're aggregating that across those big 5 basins. And then with each of the different plots that are pointed to the reservoirs, we're showing the current state of storage in each reservoir compared to what you might expect as where we are in the year with the long-term average, and then also the capacity.
Perfect, thanks. Another question, how does heavy cloud cover affect the satellite data quality? I'm happy to, or Laura, if you want to jump in.
I could start. So we do a lot of processing of the cloud cover. We have some ways to detect that and then account for that in processing data that we do on our back end as those satellite images are coming in.
Yeah, and so part of the sort of secret sauce of how we approach things is that we have an approach that's able to say, okay, if you have clouds on an image today, rather than the whole picture being unusable, we're able to pull out, what's actually visible in that picture. And then the part that's covered by clouds go back to the most recent picture that we have. So we sort of recreate images as they come in on a day-by-day basis that allows us to overall keep as current of a picture as is available of what's happening on the ground. All right, perfect. Last call for any questions. Excellent. Well, thanks everyone for your time. We really appreciate you taking the time out of your day, and feel free if you do have any more questions to just drop us a line at team@hydroforecast.com, which I'll pull up on the screen quickly for you to see. And look forward to chatting with you soon. Thanks everyone. Have a nice day.
Thank you.